So this is the material we're going to have on exam 3, just this one chapter. I can use chapter 5 in the book on gases. And you'll notice this doesn't look anything like the other slide sets because they were derived from the publisher's slides, and I just doctored them up. This one I thought was a better approach. And actually, I inherited this from, it's gone blank again. Dr. Dynack used to be here. If you, I don't know how long you've been around here. He used to be the chemistry instructor for New River. And I came here one day just to visit because I wanted to adjunct. So he showed me around. He said, oh, by the way, hand me this USB drive. Says, here's all my slide sets for the classes. I said, okay. And then I found this one was really good. And plus it had a nice intro. Okay, what's a gas? I mean, we talked a little bit about gases at the beginning in terms of how they compared to other phases. And I want to dig into gases in a little more detail. But a couple of words about gases in review. Gases are made of actually lots of particles. They could be atoms, they could be molecules, but there are lots of them in just a small space. But there are not as many in that space as there would be with liquids or solids. I mean, they're really far apart compared to the size of the particle, the molecule, the atom. The distance between them is huge. There's lots of space in there. So they act independently. They don't encounter one another on a relative basis very often. They're moving really fast. And one calculation, I think we do it a little bit later, shows that gas molecules and air molecules are moving in excess of the speed of sound. It's just that they do it for a short distance and then smack into somebody. This is an important part. When we say miscible, that means they mix uniformly. Two or more gases put together, they make a homogeneous solution, homogeneous mixture every time because they have so much space. I mean, there's room for everybody. But they do have mass. I mean, we treat them as if they don't have mass. And that's valid up to a point. You can treat a gas as if there's nothing there. But they do have mass, which means they have kinetic energy. And they, remember how we calculate kinetic energy of any object. Mass times velocity squared. Take a half of that, and that gives you kinetic energy of the particle. You can do that on any size particle. Doesn't matter how small or how big. Yeah. When you get down to the subatomic level, then it kind of falls apart. But where atoms and molecules are concerned, that formula works. And it works for planets too. So they have a certain amount of kinetic energy. And that's a consequence of not just their mass, but the fact that they're moving. If the molecules are not moving, where are we at? At absolute zero. No motion, no temperature, absolute zero. Okay, now we have to assume that their motion is random. In other words, we can't predict it. And the reason we make that assumption is we don't have the computing power to predict it. Now, ideally, if you knew the position and the velocity of every atom or molecule in a gas, you could predict the outcome of where they move and where they end up. I mean, we have natural laws that do that for us. The trouble is, there's so many particles, we don't have the computing power to do it for every one. So, and especially when gases were being investigated in the middle of the 16th century, it definitely didn't have the computing power then. So these assumptions are sort of grandfathered in. Random motion is required. We have to assume that their motion is random. Okay. We're going to look at, in this discussion, we're going to look at how the different gas laws, the laws that define gas behavior, how they work and how they interact with one. And I'll just start off by saying, if we know these 4 variables, then we can completely define a gas in a physical sense. If we know pressure, temperature, volume, and how much there is, moles. If we know those 4 factors, we can completely describe the physical character of a gas. And we're treating these gases as if they're all the same. And under certain conditions, they behave as if they're the same, at least physically speaking. When you get down to the chemistry, which we'll eventually get there, when you get down to the chemistry, then there are notable differences, obviously. But the physics of gas behavior is virtually identical at room temperature in that neighborhood and room and atmospheric pressure. So you can, that's the nice thing about gases when they were first being investigated, it didn't matter the gas. As long as you had a gas, you could treat it like any other gas. And that simplified investigations because it didn't matter what gas you had. All right. And there are going to be laws that govern those behaviors. And remember, the law just says this is what happens. It doesn't say why. We'll get to why later. We're going to treat these gases as if they were ideal. And we're going to define what ideal means eventually. You can rearrange these gas equations to solve for various factors, and they usually involve these 4. In fact, they do always involve those 4. Now, why should we be interested in gases? Well, there are a number of reasons. Some scientists don't need a reason. They're just curious. And I can identify with that. But as a practical matter, we need to know how gases behave because Earth we're surrounded by gas. And we need to know some things about the gas, even if the popular literature adulterates the message, which they have done, and politicians as well, adulterated the message of how important gases are and how they affect our present and future. This is obvious. Gases are necessary for life. We can think of them in terms of the air that we breathe. Of course, we need that oxygen. The nitrogen is just kind of a filler for us, for heterotrophs, like animals. But the other gases in the atmosphere are necessary for plants and autotrophs. Nitrogen gas, carbon dioxide. Green plants, carbon dioxide is food. It's not a pollutant like the EPA wants to call it. Definitely not a pollutant. In fact, there's adequate evidence, field research and greenhouse research, growth chamber research, all those combined, there's plenty of evidence there to show that as carbon dioxide increases, productivity of plants increases. So more carbon dioxide is not necessarily bad. I mean, the trade-offs are in favor of more CO2. We need more CO2. In fact, when you look at the historical record, I mean, if you believe that, and I do, believe the origin of fossil fuels are from buried plant material. that's been processed over the centuries, millennia, into a usable product like coal and oil and gas. Well, where did that carbon come from? Because they're all carbon-based. Carbon came from the atmosphere. At one time, there was plenty of carbon dioxide in the atmosphere. I mean, some estimates are 100 times more than we have now. And the global temperature was hot. Productivity was just through the roof. There was so much plant material being produced and so much sunlight being captured, stored in those carbon compounds, that the surface ecosystems couldn't keep up with the decomposition. So they just died, fell, they got covered with soil, buried. Now we've got them for fossil fuels. Okay. There are some gases in the atmosphere that may be considered pollutants. That's true. Carbon dioxide is not one of them. Other pollutants might include methane, CFCs, chlorofluorocarbons that we use in refrigeration units and other applications. Those are definitely pollutants. So we need to understand how gases work to get a handle on what's out there and how do we deal with it. And I've said enough about that. Global warming is a hoax. Even though the globe might be getting warm by maybe a quarter to a half a degree in the past century, right? It's not an existential threat. Okay. So let's define pressure. We all have an intuition about pressure. What is pressure, right? If your sinuses are giving you trouble, you know what pressure is. It's a force, right? It's a type of force. And the higher the pressure, the more you sense it. So when I visit a church in Mount Hope. So from Beckley, I have to go down the mountain to get to a mountain. That's West Virginia logic, I guess. Anyway, every Sunday I go down there, I feel the pressure change. It's that much of a drop from Beckley, which is about between 25 and 2,600 feet, down to Mount Hope, which I don't know what their elevation is, but it's a lot less. Or if you go to Charleston, you'll feel a change in pressure. You're sensing a change in atmospheric pressure on your senses of one form or another. So, what is pressure? Well, by definition, pressure is a force, but it's spread over an area. We define pressure in terms of a force per unit area, which means that it's an intrinsic value. In other words, it doesn't matter what the size area is, if the pressure is a value here, then if you get more area, then the force has to go up. Or if you have more force, then the area has to go up to maintain pressure at that level. Okay? It's an intrinsic value. It doesn't matter how much there is. It doesn't change. It's kind of like density that way. Density doesn't change with the amount of material you have. Now, the force changes. The force can change. But it's always accompanied with an increase in area. If the area is the same and the force increases, then the pressure goes up. Or if you take a force and spread it over more area, pressure goes down. So it's not an extrinsic property or a capacity factor. I like capacity factor better. But I'm trying to be consistent with most textbook authors. They like those big words. So when gases were being investigated, this was the second. This was the second quantifiable factor that was developed in order to study gases. The first one was volume. Volume is easy. You just need to know if it's a regular shape, then it's easy to calculate what the volume is. If you have a sphere, all you need is the radius. Or if you have a cylinder, all you need is the radius of the base and the height. You can calculate the volume. But pressure, we had a reliable measure of pressure once Evangelista Torricelli invented his device, the barometer. And initially, the barometer was used to measure air temperature. Right? All he did was took a glass tube of uniform diameter, and in the middle 17th century, that was easy to do. Glass blowers could make uniform diameter tubes, just spit them out, easy. So he had this long glass tube, and he had it closed off at one end. And then he filled this thing here with mercury. He could have used water, any liquid would do. But he discovered that if he used water, his tube would have to be 33 feet long. So he said, I need something a little more compact. So he went to mercury, which is over 13 times the density. So, okay, now I can get a short tube, manageable tube. And he had the tube, and he filled it up with mercury. And then and mercury was a common material in those days. Everybody knew it. Everybody knew it. In fact, they thought it had health benefits. Some people consumed mercury. But he filled the tube up with mercury, closed side down, and he put his thumb over it, and then he inverted it and submerged his hand in that vat of mercury, and then turned it loose. What did he find? Mercury didn't stay in the tube all the way to the top. Let's see. There's my animation. It dropped. Right? So what has he got up here? Well, he's got the first vacuum ever made. Right? By definition, a vacuum is empty space. So if you've got something in this space, to begin with, now there's nothing there, and you can't account for anything going into to replace it, that's a vacuum. Now, we know now that mercury has a slight volatility. So there are probably some mercury atoms floating around up here, but not very many. All right, and he noticed that, let's see, measured atmospheric pressure. He noticed that if he threw this thing in the back of a ox cart and went down the mountain to the ocean, then the level of mercury went up. And if he took that same ox cart and went up the mountain, mercury level went down. So he reasoned that the reason for that was there's air pressing down on this open vat of mercury. And if you go higher in the Earth's atmosphere, you have less air above you pressing down on it. And that was a correct assumption. So force is supplied by the atmosphere. Now my question is, what would happen to the height of the column if the size of the pool of mercury were changed? Get smaller or get bigger? Would there be a change in the height of the mercury column? Good question, huh? No, there won't be a change because pressure is an intensity factor. The area, surface area of the mercury, where the atmosphere impinges, if you make it bigger, then you have more atmosphere. You're encompassing a larger column of atmosphere, which has more mass, more force. So the force and the area are going up and down together, right? As an intensity factor, it doesn't matter how much you have. It's still going to measure the same atmospheric pressure. So the size of this vat doesn't matter. Okay, I mentioned that already. So we also noticed that with the weather changed, let's go down some more. Yep. As with the assumption that he made about the atmosphere being responsible for the height of this column, he noticed that if he just set the column on his desk and just left it there, over time, he would notice that the level would go up and down. Okay. And he associated that, eventually, he associated that with changes in weather. So as bad weather approached, he noticed that the column was dropping. And as the bad weather passed and it started to clear up again, the column would go up again. So air pressure was increasing with good weather, decreasing with bad weather. And we still use that today. If the meteorologist says atmospheric pressure is decreasing, then you know bad weather's on the way. So now that we've got this reliable source of measurement, we need to say, okay, what are our units of measure? How are we going to express this? Because we need to quantify it so that others can use it. And that when we talk to someone right in England, he was in Italy, if I communicate with somebody in another country, and we're talking the same language, right? They've got their barometer, I got my barometer, and I send a message and say, my barometer's been doing this, how's yours doing? And they can relate it quantitatively. Well, at that time, a unit of measure that was established was the meter. And you divide it into millimeters, right? 1,000 millimeters in a meter. Well, he noticed that if you put his meter stick next to this and 0 was right on that level, the height of the column could be judged. If this moved, if that height changed, then he would have to adjust his measuring stick to the height of that right there. And that mercury barometer right around the corner on the wall has a device just for that. It's a screw on the bottom. And before you take a measurement, you check, there's a needle that sticks down there. That's your 0 point. And you adjust that vat of mercury up and down until it just touches that needle. Now it's 0. And then when you take a measurement, you know that it's properly calibrated. So, I talked about weather already. Come on, there we go. So eventually, scientists had to agree upon a unit of pressure. And a millimeter of mercury using Torricelli's barometer was acceptable. So you could, a change in height represented a change in air pressure. Now, that's not the only unit of measure, right? Millimeters of mercury. We've got other measures for pressure, and not just atmospheric pressure, but pressure of a trapped gas in a cylinder will exert pressure on a device. And you can attach this type of device to an enclosed gas. All you have to do is close that off right there. And then have a little port here that goes over to your trapped gas. Let's draw this right. There we go. So your gas is exerting pressure here, not the atmosphere. Or if you trap it, if you don't evacuate it first, then you have to add the atmospheric pressure that was left behind when you closed it off, plus what's in here. And that's called a manometer, to measure the pressure of gas in a vessel. We use that to measure blood pressure, only we don't have a port but typically we don't put a port in your system. You can do that. My wife has had it done. They go in through a vein, actually an artery, and they run their device up to the heart for the pulmonary artery. It goes from the heart to the lungs. And they put that device in there and they measure the blood pressure at the pulmonary artery to see if you have what they call it, pulmonary hypertension. She didn't have it, but she had to endure the procedure anyway. But normally what we do when we check blood pressure is we use a modification of this called a sphygmomanometer. And it's just a cuff. It's wrapped around your arm and you pressurize it. And that pressure is applied to this. Well, originally there was a mercury column on your doctor's wall. And some offices you go into now, they still have them hanging on the wall. But they don't use them anymore. They're just for show. And what happens is your arm is in here. Right, there's your arm. And there's pressure here. Right? And your arm is doing this number. It's pulsing with each heartbeat. Right? And this is pressurized against your arms so it can sense it, just like that. And that's transmitted here to the mercury column or to the pressure measuring device. And you can use that to measure blood pressure. All right. So scientists had to agree on other forms of pressure measurement. Right? Over the centuries, we've accumulated these different measurements for pressure, for gas pressures. 1 atmosphere now is accepted as 760 millimeters of mercury. So that's a conversion factor. 1 atmosphere equals 760 millimeters of mercury. Right? Anytime you have an equivalence, you've got a conversion factor. Okay. Okay, next slide, I'm going to go into some more units measured. But for now, we can use that equivalence and convert millimeters of mercury to atmospheres. So this measurement was one, I don't know if it's actually taken or just pulled it out of thin air. But at the Raleigh County Airport, on one day, we had this much pressure was measured in millimeters of mercury. All right, convert that to atmospheres. So you're starting with 694 millimeters of mercury. You need a conversion factor that will cancel millimeters and leave you with atmospheres. And that's simple. So it's less than 1 atmosphere at 2,500 feet above sea level. You know, big surprise. You would expect it to go down for that elevation. If you go higher, right, go just, let's see, south of Beckley, the Winter Place, and get up on their mountain, you're up about 1,000 feet higher. So what happened to the air pressure then? Well, we measured it at a lower value, and it's 0.88 atmospheres. Okay, you can do that all day long. You can go up on top of Mount Everest, measure it up there, and it's going to be considerably less than that. It may only be maybe 0.6, 0.5 atmospheres. I mean, it's getting down so low that most people have to wear supplemental oxygen to get up there. Only the Sherpas that have been living there their whole life have built up enough red corpuscles that they can absorb more oxygen from the atmosphere. And in fact, when athletes are going to compete at higher altitudes, they go there for a couple of weeks ahead of time to acclimate. And it's measurable. Over that time, the number of red blood cells increases. And it's simple to measure. You just do a hematocrit. You know what a hematocrit is? Take a blood sample and put it in this little tube. Fill the tube up, and then you stick it in a centrifuge. centrifuge it down, and you measure the ratio of the height of the packed cells in the bottom to the whole total height. And that's your hematocrit. It tells you what percentage of your blood is red blood cells. For the most part, there are other cells in there, but red blood cells are the majority of it. And their hematocrit goes up with acclimation. Okay. So I'm not going to do another one. It's the same process here. You can convert from atmospheres to millimeters of mercury, just like we've always done, backwards and forwards. It's just dimensional analysis. Okay. So there are other ways to measure pressure. The standard unit, the international standard unit, is called the Pascal. And it's named for a Frenchman, a polymath. His name was Blaise Pascal. And he dabbled in gases, as did most scientists in those days. But Blaise Pascal was, he did a lot of other stuff. If you remember your math, you ever heard of the Pascal's triangle? It's simple, right? You start with 1 there. You just keep expanding it by adding these two together and those two together and these two together, and you just keep going, right? It goes on forever. It has significance in a number of areas, including statistics. But they named this unit after Blaise Pascal, and it's interconvertible with other fundamental units in the SI system. So 1 Pascal is equal to 1 Newton divided per square meter. And Newton is a measure of force. Remember, Newton is derived from Newton's second law, mass times acceleration. And mass is in kilograms, and the acceleration is in meters per second squared, right? So kilogram meters per second squared is a Newton. 1 Newton. That's a force. So that force per unit area is 1 Pascal, 1 Newton per square meter. Now, the Newton is a derived unit. That's a fundamental unit, fundamental. Newton is a derived unit. So Pascal is a derived unit from a derived unit, except for the meter. And you could argue that a square meter is derived also, because it's not length anymore, it's area. But the point I'm trying to make is these things are interconvertible. And if you find yourself in a situation where you're using pascals as pressure measurement, but the calculation requires that certain other units be there, like kilograms or seconds, and you need to evaluate that calculation, some units might cancel, right? If you just have newtons, then you don't know that you can cancel kilograms out of that. But if you can say a Newton is equal to a kilogram meter per second squared, then in that calculation, maybe the seconds cancel, maybe the meters cancel. Right? So you can interconvert if you know what they mean. All right, so Pascal is the standard unit, but most people don't use Pascal unless they're going to do those interconversions. It's more convenient to use other things like the atmosphere. So what is equal to 1 atmosphere? You can use other measurements. The height of that column, you can measure it in inches. 29.92 inches of mercury is 1 atmosphere. 14.69 pounds per square inch is an atmosphere. In fact, that's the one I learned first. I didn't know anything about this when I was a kid. We learned 14.7 psi, that's 1 atmosphere. And when we do our lab on Boyle's law next week, you'll need to know this one, and you won't need to know that one. You'll need to know the millimeters of mercury conversion to atmospheres. But you'll need to know this one because we're going to measure the pressure on the gases using a tire gauge. And they're all calibrated in psi. So you can get those measurements, but before you can do any calculations, you've got to convert them to a common unit because we've got to take into account the atmospheric pressure as well. And to do that, I'll go around the corner and read the barometer, and that will be your atmospheric pressure for that day when we do the experiment. Weathermen or meteorologists, right? We can't say men anymore, so we have to say meteorologists. That's a mouthful, actually. They've been using millibars forever. Any weather map you see, you know, the ones with the contour lines on it that show you isobars, the constant pressure is along this line. They're always in millibars. So what's a millibar? Well, a millibar is a subset of a bar. 1 bar is equal to 100,000 pascals. Right? But 1 atmosphere is equal to this many millibars. That's a quicker way to get there rather than going through this route. So 1 atmosphere equals 1,013 millibars. But 1 atmosphere is also equal to 101,325 pascals, or 101.3 kilopascals. Right? Got all these equivalents, and pressure is strange like that. It's got these are the major ones. A whole host of different conversions for pressure of gases. Okay. So we can convert these one to another. You just use your dimensional analysis. If you need to, chain them together. You'll eventually get there. Where are you starting? PSI, you want to end up with inches of mercury, right? You can go here. Atmosphere here, atmosphere to inches there. Sky's the limit. When you're doing unit conversions, you can just chain them together until you get where you're going. Just as many as you need. Yes, ma'am. Okay, no problem. Okay. Well, we're going to do some more. Oh, okay. I see where this one's going. I'm not going to spend a whole lot of time on this slide because it's more theoretical, and it just justifies what we've already understood to be an intensity property, an intensive property for pressure. It just takes this column and the density of mercury and the value of G, right? Anybody had physics? You have had physics, so you know what G is. It's like the gravitation constant for the surface of the Earth. Right? It's the G is, when we talk about mass times acceleration, that's any mass times any acceleration. But at the surface of the Earth, it's whatever mass is at the surface, and then that G is the acceleration due to gravity. So you can calculate the force on any surface, any planet, any heavenly body, if you know the G value for that planet. For the Earth, it's this. Right. Meters per second squared.
We have to memorize because in the problems it wouldn't say, it would just say like either how much force or how much mass, and then it would say, there you go, solve that. And you had to just know that since it was falling, you had to use the gravity.
Exactly. Right. Okay. So with that information, what we need to know is what's the mass of mercury being supported here, because then you can calculate what force is required to support that much mercury, right? From this point up to that height is a certain mass of mercury. Right? We use the density definition. Density equals mass per unit volume. So if we need to know mass, we need the density times the volume. So you got to What's the volume of that mercury? Right? What's the mass of the mercury? Well, we've incorporated volume in the calculation of mass in here. So eventually you get to this thing. That's how many kilograms of mercury is in that column if the diameter of the tube is 5 millimeters. Okay. So once you find the mass of mercury, you can calculate the applied force. Right? F equals ma, mass times acceleration. Let's see, is that the way they're doing it here? Kilograms, mass times acceleration is the force. Oh yes, this is the force divided by the area. Right? And you know the area here in that tube, right? Because it's a 5 millimeter diameter, you can calculate the area. Right? Pi d squared, right? Oh, 4. Let's see. Is that millimeters diameter? Yeah, millimeters diameter. Okay, so area equals pi r squared, or is substitute here r is 1/2 d, right? That's what they're doing there. 1/2 d squared times pi. And then we're just changing the units here because this has to be in square meters in order to be pascals. And actually we're converting it to kilopascals. So that just justifies the fact that this is the pressure. And if you do that calculation with a different diameter, you're going to end up with exactly the same number. Okay, because pressure is an intensity factor. Okay. I got the animations out of whack here, and there's a piece of them sitting there just waiting for its neighbors to show up. Okay, Boyle's law. We're going to talk about the gas laws now. Robert Boyle, took advantage of what Torricelli had been working on, and other scientists actually had been working on this pressure question. Torricelli invented the barometer, but other scientists were working on gas pressures and using mercury in the process. So Robert Boyle designed his own equipment, as most of these natural philosophers, they called it, did in those days. And what he designed was a J tube, right? We already know that they can make these uniform diameter tubes of any length you want. So he got a glass blower, he might have done it himself, I don't know, and made a J tube. So it's open at one end, but instead of being straight, it goes like that. And it's closed at this end. Okay? So now, he said, okay, what would happen if I put some mercury and start dumping mercury? Right? Put a little mercury in, what does it do? It puddles at the bottom. Add a little bit more. So he kept adding mercury until he added just enough to touch that inner wall. Now, this gas is sealed. Nothing gets in, nothing gets out. So what does that mean? That means the number of moles is constant. The amount of gas in there is unchanging, constant. He also conducted the experiment over a short period of time, so the temperature didn't change either. He could have submerged it in ice water, and that would guarantee that the temperature was constant. But what is actually changing in this scenario? As he kept adding mercury, he noticed that he'd add more mercury here and here and here, but he'd only get a slight increase in height on this side. So he reasoned that the pressure on that trapped gas is equal to the difference between the two heights. Just like we said, Torricelli's was the height of the column from that 0 point, the vat, up. Well, this is the bottom of his vat, and this is the height of the column. So he measures the height of the column here to be whatever, millimeters of mercury, or whatever height units you want. And that was his measure for pressure, the height of the mercury column. Now, what's the volume? Well, he knows the diameter of the tube. Right? So the height of this column, that looks too close to this. It doesn't always have to be that way. The height of this column is here. So this is, let's call this pressure, so we don't get them confused with the height of that column. The height of that column is an expression of the volume of gas in it, because he knows that the diameter is uniform, right? So a cylinder, remember a cylinder? What's the volume of that cylinder? The area here times the height here. So he knew that if the area was uniform, then a change in height meant a change in volume. And you can calculate it, calculate what the volume is. So with these two constants, moles and temperature, he let pressure and volume vary. And he noticed that when he multiplied those two values together, he always got a constant. There's the same number every time within that particular experiment. It wasn't as easy to translate these measurements to a different experiment because other factors might be different, right? If the atmospheric pressure were different that day, then you might have a different number of moles trapped in that tube. Or if the temperature changed, you might have a different starting point, or the temperature effect. So this is only valid for that one experiment. Okay. So there's his law. That's Boyle's law. Pressure times volume is always constant if temperature and moles are constant. That's a prerequisite. And nowadays, let me get this out of the way. Nowadays, if we plot that data, right, if we use units of measure that we're familiar with now, atmospheres and volume in liters. If we start off with 25 atmospheres and we say there are 4 liters trapped under that pressure, then 25 times 4 is 100, correct? But if we decrease the pressure by 5 atmospheres, we notice that the volume increases to 5 liters. Multiply those together, you get 100. And you just keep doing that and plotting the data. Right? With this should be volume. You know, that's backwards. Right? What's the independent variable here? Pressure. He's changing the pressure by adding mercury. So this one should be down here, and this one should be up there, technically speaking. Anyway, whatever the case may be, if you plot the data, whether volume's here or up there, you always get with 2 variables times each other equals a constant, you always get this shape here. And in mathematical terms, that's called a hyperbola. And you remember the characteristic of a hyperbola? You keep drawing it out here, never touches the axis. Drawing it up here, never touches the y-axis. I always thought that was strange. Are you sure about that? I used to think, I didn't confront my teacher with it, but I was wondering, how do they know it never touches? Has anybody gone out to infinity yet? It's a theoretical proof, I guess.
It's like, but basically it can't be 0, or when it equals 0, that makes it undefined, so it can't touch the
There you go.
line.
I knew there was a reason for that.
So it'll have an essence of
Oh yeah, that's right. Right. Let's make one of these 0. Right. It no longer has a meaning. Good, thank you.
I have to know that. I just have to.
Right. It's been too long for me. I forgot half of what I learned in calculus. All I remember is how to calculate the area under a curve. Or, no, I can do derivatives too. And what they mean in the physical world, the relationship to the physical world, the relationship of distance traveled to velocity to acceleration. Anyway, let me get back to this topic. Okay, so since this one times this one equals a constant, notice that when pressure goes up, volume has to go down. Or when pressure goes up, volume goes up, pressure goes down. They're inversely related. And if you draw a smooth curve here, a best fit line, I hope you can do better than that. Notice that anywhere on this point, if you draw a tangent to that line, the slope is always negative. Now the slope changes with the curve, right? That's a given. But anywhere you draw a tangent to that line, that's known as the instantaneous slope at that point. That's calculus too. The slope of that line is always negative for an inverse relationship. Whenever you have two variables equal to a constant, their product is equal to a constant. That is an inverse relationship. But I may have said it before, scientists hate curves. When we can make a straight line out of the data, we do it. Well, fortunately,
Nobody likes those.
no, not if you can help it. Sometimes we have to, but when we can get away with it, straight lines are easier to deal with. So if we take this pressure times volume equals a constant, notice what happens if I do a mathematical transformation that's perfectly legal. I divide both sides through by volume. Right? I can do that. That means this one cancels. And this one now is equal to K divided by V. I don't like it like that. I'd rather factor out. So K times 1 over V. Okay? I'm still legal. Now, what would that look like plotted? Y equals slope M X. If you had B in there, where would B be? Well, B would be right here. Right at the origin. It's equal to 0, so we don't put it in there. So now if you plot pressure and 1 over V, then you get a straight line. We're going to be doing that next week too. Wait a minute. We've already done that, haven't we?
Was that our first lab?
Yeah, graphing techniques. I thought I was telling you something new. You've already been exposed. Better wear a mask. Okay. All right. As long as there's no change in temperature of the moles of gas, this holds true. But like I mentioned earlier, this relationship isn't very useful because it only holds for that one experiment. P times V equals a constant. And it's a little difficult to manage unless you calculate the constant and then you can solve your equation for an unknown. Say if you know the volume, then you can solve it for the pressure, vice versa. But there's a better way. If you know that the initial conditions are a certain pressure and a certain volume, then you change one of them. In the same experiment, you change to a different pressure. Now, why is that equal? Why are these two equal? Because in that experiment, This expression is equal to the constant. But when you change something, it's still equal to the constant. Right? So that means they're equal to each other. This is the before-after version, I call it, of the gas law. Initial, final. And we're going to use that reasoning for the other gas laws as well. But this is the way that Boyle's law looks. Initial pressure volume equals final pressure volume. And if you know 3 of those values, you can solve for the 4th one. All right. So here's an example, but I'm probably running out of time anyway, so I'm going to skip it up. We just have these values given to us, and which one's missing? Millimeters of mercury liters is missing. So we're going to solve for the final volume. Okay. Just plug in your values. And you find out that if the pressure changes from that to that, you're going to get an increase in volume for 1560. Okay, let's see. And you can do it a whole host of different ways. You can either solve for the unknown in that expression first and plug in the numbers, or you just plug in the numbers and then solve the unknown. It doesn't matter. Whatever you feel more comfortable with. Okay, Charles' law. Charles was a Frenchman. Right? These guys, Jacques Charles, he had 2 first names. That's the way I look at it. In Charles' law, he is allowing the temperature to change and measuring the volume as a result. So the variables here are volume and temperature. So which 2 have to be constant? The other 2. Pressure has to be constant. Mold has to be constant. If you can hold those 2 constant, then you can let these 2 vary and see how they react to one another. And as it turns out, volume divided by temperature is a constant in Charles' law, which means if this is always constant, then if the temperature goes up, the volume has to go up. Okay, that's a direct relationship rather than an inverse. Okay, so this is the data that Charles got for his measurements with gases. Temperature down here, volume here. Now that's correct. He changed the temperature and watched the volume change. So if you plot them, you get a straight line already. Because here it is, y equals mx. So you've already got a straight line with a direct relationship like that. But did I mention this earlier with temperature discussion in previous chapters? How Kelvin came up with his system.
I think so.
Yeah. So what Kelvin said was, and Kelvin derived his temperature scale from thermodynamic considerations. And he went into great detail and referenced some masters of thermodynamics of his day. In the paper, I've got a copy of his paper. It's kind of difficult to read because of the way they wrote things back then. But he reasoned that when you're making these calculations, pressure is always a positive number. You can't go less than 0. Moles is always a positive number. Can't go less than 0 there either. Pressure, moles, volume. Volume is always a positive number when it goes into calculations. But temperature, with our temperature scales of the day, you could get negative values. If you try to put those into calculations, you find out that things get really screwy, right? Like what would happen here if Charles measured things at -°C, right? A negative divided by what would give him the right answer? It wouldn't. right? Because now the constant is going to be a negative value. So Charles' law, the way he wrote it here, is only good for positive values of Celsius. So Kelvin reasoned we need a system where there's only positive numbers. So that's when he decided to find out how to make positive numbers. And he did it by extrapolation. You can't get these values to go much lower, right, when you plot them. I mean, you can get them down maybe into here, but you can't go all the way down to absolute zero. So we had to be theoretical about it and just extrapolate the line down to where it met zero volume. What would happen if you had zero volume gas? And an ideal gas is supposed to do that. Ideal gases are supposed to stay gases all the way down to zero volume because we're ignoring the existence of the particle itself. Right? We know that's not true. But Kelvin extrapolated down to this baseline at zero volume and found that minus 273 degrees Celsius would give him zero volume. So he said, okay, that's my 0 point. Nothing gets colder than that. You can't get below that. That's my 0. Everything else is a positive number. So we're good to go. And in fact, anytime you do calculations in chemistry or physics, if you're going to do them with a few exceptions, and we'll talk about those at some future point, but just assume that you've got to convert to the absolute system. And for Celsius, that means go to Kelvin. Okay. And if you do that, then you can run this down all the way to zero, absolute zero. And the relationship still holds. You don't have to worry about negative numbers anymore. All right. So we can treat Charles the same way we did Boyle's before and after. The before situation is VI over TI. And VF over TF is equal to the same constant. So now we can set them equal to each other. Okay, so there we have another before-after relationship. And the same thing holds. If you know 3 of them, you can solve for the 4th one. Just like any equation, if there's only one unknown, you can solve for it. Okay. There's one more law after this one. Let me see. We're going to do, we got some examples. And I'll just point out that whenever you're given a Celsius temperature, you better convert it to Kelvin. Otherwise, this will not work. So I'm going to skip these. You'll see them again later. And I've got review documents. You guys didn't say a word. I just started talking. You're sitting there watching. I got all these handouts that I could have been given. Oops, not that one. You've already seen that one. And then I've got the usual review document. Did I give you two? Yeah. Lots of repetition, as usual. And there's the work problems. So you get plenty of practice working these problems. So we're not going to spend a lot of time on them now. Next week we'll review all this stuff and work from those documents. Okay, the third law is Avogadro's law. Avogadro was interested in what happens to the volume if you actually change the amount of gas that's crammed into a space. Okay. So he wanted to say, what's the relationship between these two? Well, actually, it wasn't entirely Avogadro. He had other people interested in it also.
In fact, one of his students actually took the ball and ran with it. Now, I'll describe that in just a second. But when you're watching the change of volume with a change in number of moles, you have to hold the other two constant, temperature and pressure. Those have to be constant in order to watch this happen. So how would you do that? Well, I can think of one way. You need a cylinder with a piston in it, and then some mass that you put on top of that piston. And it will reach an equilibrium point, and then you'll have a volume here. Your first volume. And then what you do is you have a valve here on the side. And you are able to inject known amounts of gas in there in addition to what's already there. And you watch a change in volume. And what he found was that the relationship between volume and number of moles is direct. In other words, the quotient, again, is equal to a constant. Oops, clear that out. And if you plot the data, you'll find it's got a straight line again, a positive slope straight line. And the before and after works just like this, the previous two laws. Initial volume divided by initial moles equals final volume divided by final moles. And always the other two factors have to remain constant. If they change, then we need another approach. And I'll show you that in just a minute. Okay, so we're solving for various factors. Now, the interesting thing about it is this law and later laws that I'm going to introduce can be used to help us with stoichiometry, right? When you're getting at the number of moles, now you can apply it to chemical reactions. So this chemical reaction, where ammonia decomposes into nitrogen and hydrogen, if we know that the volume initially is 35 cubic feet at 25 degrees C, let's see, calculate the volume after the decomposition. Now, you may wonder, I don't have enough information. They didn't say how many moles were there. Right? They didn't say anything about that. We just gave you the balanced equation. Well, there's your moles. Right? These are all gases. Total moles on this side is 2, right? Total moles on this side is 1 plus 3 is 4. So before moles is 2 and after moles is 4. So you just plug them in here. Before moles, after moles. Initial volume is 35. Solve for the unknown. So this is what it looks like once you solve it. Now we know that we're going to have 70 cubic feet of gas after the reaction. And it makes sense. It doubles. It goes from 2 to 4. So the volume has to double. Okay. Now, suppose more than one before and after changes. You have a potential for volume, moles, temperature, and pressure to change during a process of any kind. What do you do? Well, if you know the before situation and you know some all but one of the after situation, you can solve for it. But we need an equation to do that. So if we look at Boyle's law first, right? And then we say, okay, but look, that volume has a relationship to temperature too. This one's related to temperature in that way. This one's related to temperature in that way. So now we got an expanded equation that includes both Boyle and Charles. We can do the same thing with Avogadro, right? What's Avogadro's relationship? Volume to moles. So volume to moles, we just stick it in there. Now we have a combined gas law. So using this one, as long as we know all the factors except for one, we can solve for it. Even if they're not held constant, they can all change. So you have to know everything except for one factor, and then you can solve for that one. And that's real world. Okay, we're going to get even realer now. Suppose you have a situation where you're not in a before after. You're in what's called a state. I know what I have right now. I don't know how I got there or where I'm going. This is things right now. How do you solve that problem? You need a derived equation from the gas laws. Okay, this is going to talk about ideal gases. I think we need to. The stream of consciousness works better. So let's back up there. Let me talk about it. We had what? Initial moles and temperature, right there. And that's equal to the after. But it's also equal to a constant, right? Because it works the same way. The only reason that the before and after are equal to each other is because they're both equal to the same constant. So instead of putting the after, let's just put constant. Right? It's equal to a constant. Okay. So now, if we know what each one of these is in relation to each other for any gas, then we can calculate that constant for any variations here. So let's say we say 1 mole. Okay, let's keep it simple. 1 mole. Right. Let's pick a standard temperature. Right. For gases, the standard temperature is 0 degrees Celsius. It's only true for gases. Everybody else, standard temperature is 25 degrees. But for gases, it's 0. So 0 would be what? 273.15 Kelvin. We got to convert it. So what's the pressure? Well, I'm going to say 1 atmosphere. Okay. So we got a mole, we got an atmosphere, we got temperature. What's the volume? That one you have to measure. So what's the volume under those conditions in liters? The volume in those conditions in liters is 22.4 liters. So now we have all of those values equal to a constant. So what does that calculation come out to be? Well, actually, it's 0.08206 liter atmospheres per mole K. Right? Liter atmospheres per mole K. Those are the units. And then this just resolves those values right there. So this is given a special, it's called R. That's a gas constant. So now that we know what this is, with those units only, then if we know 3 of these, we can solve for the 4th one. And it doesn't matter how it got there. That's our state function. So you usually see this written as PV equals, bring these two over here next to the R, N, R, T. That's the ideal gas equation. Okay? So you can use this value of R as long as your units here are atmospheres, liters, moles, Kelvin. Then you can use that constant. In any other circumstance, if you want to use R for some other calculation, you got to take into account the units of measure and find the R that fits those units of measure. Sometimes we use R's in equations where you're calculating energy. In that case, you need a different constant with joules in here somewhere. Okay. All right. So let's get back to the slide set. And there'll be another slide with all that information on it, but it was just out of order, I think, for my discussion. So let's go back. What's an ideal gas? Well, it's a perfect gas. That's circular logic. You know, ideal is perfect, perfect is ideal. So what is it? Well, like I said earlier, an ideal gas remains a gas under all conditions of pressure and temperature. It doesn't matter how much pressure or how cold you get it, it's still a gas. Okay, that's one condition. And in order for that to happen, you have to assume that a gas molecule has a point volume. Remember mathematics? Point. No dimensions. No width, no height, no depth. That represents no dimensions. So when we say point volume, we mean the gas molecule has no volume. Okay. When it's moving around with its lack of volume, if it encounters any other gases, there's no interaction whatsoever. There's no attraction, there's no repulsion. If anything, they just smack each other like billiard balls, bounce off. That's it. No interaction whatsoever. And of course, they have to obey all the gas laws. That's a given. If they don't obey all the gas laws, then what's the use of a law? It's like saying, define an ideal criminal. It disobeys the gas laws, right? Or disobeys the laws. But in reality, gases do liquefy, and some of them solidify under pressure and decreased temperature. A perfect example, dry ice. I know what's dry ice. It's solid carbon dioxide. Or I used to use liquefied nitrogen and liquefied argon too. Right? All you have to do is compress them and get them cold enough, and they'll turn into a liquid. In fact, nitrogen is really cold, minus 195 degrees Celsius. Very, very cold.
Can't you, isn't the only way for hydrogen to be like not a gas under like a lot of pressure, like in the middle of stars and stuff?
Oh yeah, yeah.
Because I've seen like a chart that was like hydrogen stays a gas and like every temperature, and it can only be like a different state when it's compressed in like the center of stars and stuff.
Yeah, there's even some speculation that near the center of Jupiter, they have a new form of hydrogen called metallic hydrogen. It forms a liquid, but it behaves like a metal. Yeah, there's some strange situations out there that fortunately we don't have to deal with in this class. But they're interesting to speculate. All right, so those are real gases. They do have volumes. I mean, we know that. And actually, we can measure the volume of gas molecules. And they do interact with one another. Right? Some gases attract, some gases repel. And that affects their behavior. And they do interact with the walls of the container. That wasn't a condition up here. Ideal gases don't interact with anything, even the walls of the container. Well, it's a good thing that they do interact with the walls of the container. Otherwise, we couldn't measure the pressure. Right? You bore a hole and put a gauge in there. If they don't interact with the walls, they don't interact with gauge either. And you might as well say, oh, there's no gas in there. Right? It's a vacuum. but it is. They do interact with the walls and with measuring devices. Now, there are conditions under which gases do behave more or less ideally. And those include low pressure and high temperature. Let's take temperature first. Now, how would high temperature simulate ideal behavior? Well, if molecules are coming at each other with really high energy, that means they're moving fast. And the time that they have to interact is reduced. In other words, they impact with one another and bounce off with no time to interact. So that mitigates this, interaction problem. It also means that at high temperature, they're more likely to be gases anyway, right? Because we know as you add energy to a liquid, it turns to a gas. So if you get the temperature high enough, any liquid will become a gas. Low pressure. Low pressure also mitigates this interaction problem because they're very far apart. Low pressure means the molecules are extremely far apart. They have very seldom interact with one another. Now, what are conditions of low pressure and high temperature? Well, as it turns out, high temperature is room temperature, right? High temperature relative to what? Relative to absolute zero. 293 K would be 0 degrees, right? 313 degrees would be 20 degrees Kelvin. Oh, no, I'm sorry, that's 20 degrees. 273 would be 0. How about pressure? 1 atmosphere pressure is considered low, right? And that's by empirical. I mean, we've experimented and found that this 1 atmosphere satisfies this condition. High pressure would have to be like 100 atmospheres, 200 atmospheres, 300 atmospheres, at the bottom of the ocean. Okay. Oh, so this is the ideal gas equation. I didn't give credit to the person who first proposed it, Emil Clapeyron. You may see him again when we get to energy relationships and chemical reactions. So there's your ideal gas equation. And it has various constants that can be applied. This is the one we discussed earlier. As long as liter atmospheres, mole K are your units of measure, this is your gas constant. But if you have a gas constant that has pascals and cubic meters instead, then it's going to be this one. Or if it's joules, it'll be this one. Okay? So I'm assuming, since these are identical on the denominator, that 1 Pascal times 1 cubic meter is equal to a joule. Pressure volume. We'll look at that a little later. Let's see, wait a minute, in this class? Yeah, I think we do get to that. Talk about thermodynamics. Okay, so that's what you do if you don't have a before-after situation. If you're in a state, then use the ideal equation. And you just have to look at the problem and say, what information is given me? What type of problem is this anyway? Is it a gas law problem? And then you say, okay, do I have a before and after situation? Is there information in there leading that direction? Or is it just a state? If it's a state function, then you go to this one. Okay. And these are just various solutions, right? You can rearrange the equation for whichever unknown you're interested in. We've even worked problems in the past. Maybe we'll get to one in this class where you're interested in ratios. Right? What's the ratio of, say, volume to moles? So now you put the moles over here, and you only have to solve for this part of the equation. If the question is, what's the ratio of volume to moles. So you can solve it any way you want to. Oh, I forgot that was there. Yep, the moles to volume. And you can solve for R, right? If you use different values in here and you know what they are experimentally, then you can calculate your own R. Or you can verify an R. Or you can plug in that R 0.08206 and say 1 mole, 273, 1 atmosphere, and calculate what that volume is. And it should come out to 22.4 liters. Okay, so here's a solution to a problem in a state situation. Calculate the pressure of a system. 2 moles of gas at 37 degrees occupies a volume of 50 liters. That's a simple example. You can calculate the pressure as long as your units are right. Moles, you have to change that to K, and you use liters. So here's the change to K, and you can solve for pressure. And this pressure is in atmospheres. If you need pressure in different units, then you just take that and convert it using those equivalences that we showed you earlier. And they should be in the review document and useful information in the back. Should all those conversion factors. Okay. Let's see. How am I doing on time? I sort of lost track. How much more time?
15 minutes left.
15 minutes. Okay. Stick around if you can, leave if you have to. I'm going to finish this discussion, and you can watch the rest of it on the recording. Actually, I can say that with more confidence now that we've got higher resolution available to us.
We gotta leave on the time, so.
Okay, I understand. Okay. So in this case, we've got this reaction to consider. You got a solid here, a liquid here, and there's your only gas. So really, we don't have to consider these. Or we can say they have insignificant volume. As a general rule, now this is not hard and fast, but a rule of thumb, I should say. When you take a liquid and turn it into a gas, the increase in volume is in the neighborhood of 1,000 to 1. Okay, so it's a huge increase. And of course, that varies with real situations. Calculate the mass of mercury 2 oxide needed to produce 220 cubic centimeters or 0.220 liters of oxygen at 25 degrees C and 740 millimeters mercury. Right? That's a stoichiometry problem. So what do you need to know to go from here to find out what mass is that? You need moles, right? So do we have the information to calculate moles? Let's see. We got pressure. We got volume. N is the unknown. R is our constant. And T, PV equals nRT. So the only unknown in that equation is moles. We can calculate how many moles of oxygen this represents. And then we can work backwards to the mass of HGO. Right? And that's what this does. That's the number of moles. Oops, went too far. There we go. It's too slow. There. That's the number of moles of oxygen. Now we can do, right, if that's 1 mole, if that's 1 unit, then twice that will be the number of moles of HGO, and then use molar mass, convert that number of moles to mass, and that's what this one does. Okay. So we know that we had to start with 1.9 grams of HGO to give us oxygen with those conditions. Okay. And then again, what is it saying? What volume of mercury was produced? Actually, not what volume. What volume of mercury was produced? Okay. It's going to be the same number of moles as this, right? Because these are 1-to-1. So now that we know the number of moles, we find what's the mass of that? Here's the mass. And then convert that mass using density into volume. And that'll tell you the volume of the mercury that was also produced. So when you decompose this stuff, and this is red, it's obvious, I mean, it's bright red. And Renaissance and modern scientists knew how to do this reaction and produce oxygen. Like that's what Lavoisier did when he characterized oxygen. Anyway, now we can use, remember when we were talking about composition? I mean, calculating the empirical formula and the molecular formula for a compound, right? We did that, didn't we? Okay. The empirical formula you can do with mass percent, right? But in order to make the jump from empirical to molecular, you need to know the true molar mass of the compound. And you compare the empirical mass to the molar mass to find your multiplier, right? Remember that? Okay, this is one way to find the molar mass. You need a method to find the molar mass of your compound that is independent of its actual composition. Right? We call those colligative properties. You need to be able to use colligative properties to determine the molar mass of a compound without knowing what it is. Okay, and Dumas method is one of them. We're going to do that. I think that's the last lab on our agenda. The Dumas method uses the ideal gas equation to tell us how many moles of a volatile compound are trapped in our Erlenmeyer flask. And we have measured that flask before, and we measured after with the condensed gas in it. So we know the mass. And then we use the gas law to tell us how many moles that represents. And then calculate the molar mass per volume. Mass per mole. Okay. So that's where, in fact, this relationship, I call it molecular weight. Mass per mole. That's it. I mean, it's just defined that way. So if you're working a problem that says, what's the molar mass of this compound? If there's not a simpler way to determine it, I mean, if you don't already have the information, then you say, all right, I need mass. Do I have it? Okay. Usually you do. Moles. How do I find the moles? Well, it depends on the experiment or the problem that's given to you. So that's the real kicker. How do you find the moles? And it just depends on the problem. If it's a gas law problem like this, you can use the Dumas method, find the moles. If it's a different problem like titration, right? I think we're going to do that. Titrate, find the molar mass of citric acid by titration. I think that's in the agenda. Then you find out the number of moles of the citric acid by titrating it with a known concentration of base. Okay, and that gives you moles. So we're always heading to the same place, molar mass, and we need mass and moles. It just depends, how do you get the moles? Mass is easy, you just stick it on the balance. The moles is the trick. All right, so Dumas method was proposed by this fellow, Jean-Baptiste André Dumas. And that's not the same Dumas that wrote Three Musketeers. It's a different Dumas. Okay. Let's see. Well, you don't need to worry about all this information. He was really big in organic chemistry and organic analysis. And he used this method to determine molar masses of numerous organic compounds. The one condition in this method is that the compound be volatile at room temperature. So its boiling point has to be very close to room temperature, so that when you heat it up slightly, you volatilize, you make it into a gas. Then you can use the ideal gas equation to find the moles. I mean, if it's not volatile, you couldn't use this method to find the molar mass of, say, well, I don't know, table salt. Because you got to get table salt up into thousands of degrees to make it volatile. Okay. Now, what we're also going to do is combine these two equations, universal gas equation and molar mass equation, and produce a single equation that will spit out the value for molar mass. And notice that if we know the mass and we solve this for moles, then we substitute its equivalent into that position. So that's what we're doing. Oops. There we go. So molar mass is equal to the mass of the compound times gas constant times temperature divided by pressure volume. So that way, you can do the whole thing in one calculation. You just have to get these values, temperature, pressure, volume of the gas, and its mass under those conditions, and you can solve with one equation. You can do it this way. You can do separate calculations, but why bother? You can do it in one. As long as you understand where it came from, that's important. All right. This is an example of the Dumas method. I'm going to let you look at it on your own. We're going to get more of it when we get to actually determining, in the lab. And this says, what compound is it? Doesn't say that. It just says a compound. So the molar mass of that compound is 152.98 grams per mole. Okay, is this another example? All right, this one is actually a before and after problem, I think. There's liters. Calculate the final volume. Okay, so we got an initial volume, we got a temperature change, we got a volume. Okay, so we're using before and after here. But what else are any of these values constant? Let's see. Yeah, moles is constant. Moles doesn't change. So moles is a factor that drops out, right? If moles is constant, then your equation becomes PV over T equals PV over T. Right? Am I not going to show? Oh, yeah, there it is right there. Right? They cancel out because they're equal. And then our calculation gives us the final volume, 23.75. Okay. Let's see. This one, calculate the final pressure. Right. So we can use this situation to solve for the final pressure, and the values for moles here come from the coefficients of the equation. Since they're all gases, then the relationship is 2 moles over here, 4 moles over there. There it is right there, 2 moles to 4 moles. And now we can find out what the final pressure would be. That's not as interesting as, I guess I'm not going to use it. I thought I had nitroglycerin in here. It goes from no gas liquid to 19 moles of gaseous products. So that rapid increase from no moles to 19 gives you its explosive force. Okay, Dalton's law of partial pressures. It's really simple. This is the same John Dalton that introduced the atomic theory. And what he said was, when you measure the pressure of a mixture of gases, the total pressure of a mixture of gases is due to the individual pressures that would be exerted independently by each one of those gases. Those are partial pressures. So if you have a mixture of, let's say, nitrogen and oxygen, 20% oxygen, 79% nitrogen in the atmosphere. 1 atmosphere pressure is due to 0.2 atmospheres pressure from oxygen and 0.79 atmospheres pressure from nitrogen. That's not 100% though, is it? It's not 1. So where's the other 0.01 atmosphere pressure? Most of it is argon, with a few minors. But total those up is 1 atmosphere. The total is due to the partial pressures of each of the components in the mixture. Right? And this is an explanation. It just goes through the ideal gas equation to show you that the pressure total, these are individual pressures. Well, that's the total pressure. These are individual calculations for each of the gases. Right? We just substituted the solution to the ideal gas equation in terms of pressure into these factors here. What's the same? Well, R is the same, temperature is the same, volume is the same in every one of them. The only thing that changed is the moles of each one of them. Right? So what we have is the proportionality of pressures is due to the proportionality of the moles. So if you know the partial pressure of a gas in the mixture, you also know its mole ratio with the total. Okay? So if we know the total number of moles of a sample of gas, of air, then we know that 0.2 fraction of that total moles is oxygen. That's also known as mole fraction, right? It's got a big X here. Actually, it's hard to do that, have the real one that they like to use. A fancy curvy X is mole fraction. Right? And that's all it is. It's just a ratio of the moles of the individual gas to the total moles. And that's also is equivalent to the pressure, partial pressure of this gas to the total pressure. Okay? And all the partial pressures have to equal 1. Because they're fractions, they have to add up to the total, which is unity. Okay. Oh, here's my, yeah, there we go. That's nitroglycerin. Actually, they're starting off as a gas. That makes more sense when we're actually talking about gases. That'd be a nice trick, though. I mean, how do you get nitroglycerin to be a gas? You have to heat it up, don't you? I wouldn't want to be the one heating up nitroglycerin. But somebody does. They probably use very small amounts. Because a pinhead size of nitroglycerin would probably blow that bottle of water apart if it detonated. Okay, so we go from 4 moles of gas here to 19 moles of gas here. So that's a huge increase in volume. And we can calculate the partial pressures of each one of those gases. The total pressure is going to be this, right? Under these conditions. Under those conditions, the total pressure is going to be here. Okay. But we're starting at what? We're starting at 20. And the total's here. So what are the individual pressures? Well, this total pressure is due to 19 moles of gas. So 1/19 is oxygen. 6/19 is nitrogen. 10/19 is water, and 12/19 is carbon dioxide. And that's what this slide shows, I think. Here we go. Oh, I'm sorry, not 19, 29. I can't even count. Well, 22, 28, yeah, 29. Oh, well. I failed my own exam. So, and these should all, let's see, one more, right? These should all add up to that pressure. And so if we add them all up, we get pretty close. Calculation error, rounding error. All right, we're getting pretty close to the end here. We're going to try to explain why these gas laws work, why gases behave the way they do. It is called the kinetic molecular theory of gases. In fact, this theory was first developed for gases to explain their behavior, but it's since been found to be accurate for explanations of how liquids and solids behave as well. So the kinetic molecular theory requires that we have certain postulates that must be obeyed and observed in order to explain gas behavior. One is large numbers of particles called atoms and molecules, right? That was the first slide, we said that. The particle size has to be small compared to the distance between them. It doesn't say that it has to disappear, right? It just has to be very small in comparison. These gas particles are moving very fast. And when they collide with each other, which is inevitable, even though they're very far apart, they will eventually collide. Right? When they do that, and they collide with the walls of the container, they transfer kinetic energy, right? From one to another, right? They conserve their momentum. Right? Physics. Mass times velocity is momentum. So the total momentum before a collision has to be the same after a collision if it's totally elastic. And under these circumstances, we have to assume that it's elastic. Right? If it's not elastic, if it's inelastic, then some of that energy is converted into heat. But actually, that doesn't matter, because what is heat? What is temperature? Temperature is a measure of the average kinetic energy of all the molecules in that gas. Right? So it's really a moot point whether it's elastic or inelastic. And that there's no interaction of the particles, right? Their collisions are just like billiard balls. They just bang into each other, bounce off. Okay, so here's an example. For simplicity's sake, we're going to say these 7 balls weigh 5 kilograms. And I think 5 kilograms is probably close to the average adult bowling ball, something like that. 2.2 times that would be what? About 11, between 11 and 12 pounds. Right. What's that? What's the adult ball? It's heavier than that, isn't it?
It's probably 8 to 15.
Okay. I tried bowling a while, years and years ago. I mean, it was fun. But once I got finished with it, I couldn't play my saxophone. It just ruined my hands for about a week. So I said, okay, I got to make a choice. No more bowling. Okay. What's the kinetic energy? That's EK. I'll write it KE, but EK is kinetic energy here for each of the balls. Right? So we calculate it as mass times, let's see, kinetic energy is 1/2 mv squared. V squared would be meters per second, would be meters squared per second squared times the mass. So that's joules. 1 kilogram meters squared per second squared is a joule. That's energy. Okay, so when we do our calculations for our 7 balls, they're moving at different velocities. They're not interacting with each other. We're just calculating individual energies. We calculate the individual energies for each one. We get these numbers in joules. And then we want to know the average kinetic energy of those 7 balls. So we just average this together, right? I thought we were going to do that. Oh, okay. First, we're going to say, okay, what if we take the average velocity of these 7 balls at 40 meters per second and say, okay, let's assume that that average velocity is good for any one of these balls. So what would its kinetic energy be if the average is 40 meters per second? So we just introduce that. Well, I should have looked at the slide a little more carefully before it came up. It's messing with my discussion. Okay, here we are. Now we're doing the average kinetic energy. 5,000 joules is average kinetic energy for one ball. But if we take this and use it to calculate 1/2 mv squared, let's see, here. No, we're going to take this average kinetic energy and say, what would the velocity have to be? What would the average velocity have to be in order to calculate that value? So that's why we solved this equation for V and plugged in this value here, there, and the mass of one ball, and its velocity would have to be 44.7 meters per second to give us this average energy. So there's the discrepancy. If we use this, we would get a lesser value. We need to use that value. Okay, so where am I going with this? I've been dancing around the barn a couple of times. We need a different estimate for this value. We can't use an arithmetic average. It just doesn't work. So we use another procedure called the root mean square. Okay, it's just a mathematical averaging technique. And as it turns out, the root mean square of these velocities will give you that value. So what do I mean by root mean square? Okay, let's do that. Root mean square, work backwards. If you have these values, then the first thing you do is square them. Right? So these are a set of values. Let's do it this way. We have velocities here. Take those and square them. So you get another set of numbers. Okay? Then you take the mean of those values. That's what that bar means in statistics. A bar word means the mean. So take the mean of these squared values, and then you take the square root of that. That's the root of the means of the squares, root mean square. Okay? When you do that, you get that 44.7 meters per second. And then if you use that in the calculation for kinetic energy, you get a true value for average kinetic energy, which is proportional to temperature. Yeah. Oh, yeah. Go ahead. No problem. I'm close, but probably not close enough to the end. See you next week. Okay. Oh, okay. So now we're going to look at a particle in a box. That sounds like Schrodinger. What was that? Schrodinger's cat. So we're going to put a particle in a box. If we want to address the energy of that particle in terms of kinetic energy, we've got to do it in 3 axes. Because it's moving in this direction, but in our frame of reference, it's moving a certain speed this way that way, and this way, that way, and this way. 3 axes for our kinetic energy. Okay. And the total energy for it is the energy on that axis, energy on that axis, and the energy on that axis. Mu here is the velocity on that particular axis. Now, if we have a mole of those particles, right, and we can say this is the same for every particle, right, on those axes. They might be moving in different directions, but if they're moving real fast this direction, they can't be moving fast that direction. But if they're moving like this, they're moving faster that way and lesser this way. So it all evens out. So we have a mole of them. So now the kinetic energy for all of that mole is this value. So how did I get from there to there? I don't know. I think I made a jump here without doing the calculations. Probably because the calculations are too massive to accomplish. So let's just go straight to the heart. This root mean square of these values here will give us a velocity there. The root mean square of velocity of all our particles is equal to this calculation. And here's the gas constant. Here's the temperature in Kelvin. Here's the molecular weight of the particle. Now, the problem is that the molecular weight has to match the units of measure for these. Right? So that means it can't be grams per mole. It has to be kilograms per mole, because kilogram is the standard that goes into calculating that value. And we're going to have to use this standard here. I mean, this gas constant here. Because ultimately we're talking about energy. So we're going to use this one. All right. So let's do it for air. Calculate the average velocity of air at 37 degrees. Well, air is a mixture already, right? So we're going to have to compromise. We're going to have to calculate what would be the average molecular weight of air, right? We use that weighted average concept for calculating the molar mass of an element with all of its isotopes. It's the same type of thing here. So we come up with an average molar mass of air of 29.02, right? So nitrogen would be what? Well, oxygen O2 is 32, and nitrogen is 28, roughly. But this is only 20%. And this is 0.79%. So we come up that is 29.02 grams per mole. Okay, now that we have that average molar mass, that's the value that we can plug into the formula. But it needs to be converted to kilograms per mole because of the R that we're using. All right. So now we can substitute in this value here. We can substitute in that value for R here. And we need to know the temperature, 310.16 K. Okay. Now we can calculate the average velocity for air. There. 516 meters per second converted to miles per hour is 1100. Right. What's the speed of sound at sea level? It's in the neighborhood of 750 or 60 miles per hour, I think. So it's moving faster than the speed of sound. Let's do the same thing for helium, right? Helium's got a different molecular weight at the same temperature. So what would happen? Since helium would be a smaller value here, that means its velocity is going to be higher, right? Because it's in the denominator. And it turns out it is moving faster. 1,390 meters per second. Or, oh, we didn't do miles per hour. Okay, so it's over twice as fast. That's why when you breathe helium in, your pitch goes up because the molecules are moving faster. And pitch is all about speed of the sound wave. Right? And I had a student tell me the other day that it was in my Logan class. He said he thought he saw an example, like a YouTube video, where they used a different gas that was heavier than air, and the pitch of the voice went down.
Yeah, I've seen this.
Seen that? Okay. I don't know what gas it was, though.
It was boron,
Really?
I think so.
Boron. Okay, boron is 10. Okay, boron by itself won't do it. It'd have to be a boron-based compound, right?
I can't remember the exact.
Yeah, it must be. I mean, if we follow this scenario, it would have to be a heavier gas molecule. I was thinking maybe an inert gas. Like, what would be heavier than 29? Let's see, it won't be neon. Neon's 20. Maybe argon. Argon's almost 40. I bet that would work. You want to be sure, and they said they had to turn themselves upside down for it to get out of their lungs because it was denser than air. They couldn't just expel it out. They had to invert themselves and breathe heavily to get it out. Well, anyway, so we're going to use, in fact, Graham, this fella, uses that relationship, that velocity relationship with the molar mass as a way of determining molecular weight for an unknown gas. If you know the molar mass of a gas and you can compare it to the velocity of another gas, then you can use the calculation to determine the molecular weight of the unknown gas. So there's another way to get at molar mass without even knowing what the gas is. It's called the law of effusion, or more commonly, the law of diffusion. And it uses this kinetic molecular theory relationship to compare these two gases, any two gases. So he put this relationship together, and there's the velocity of one gas, there's the velocity of the other, and here's the velocity equivalent for one gas, and here's the velocity equivalent for the other gas. Notice that there are cancelable values in here. First of all, we can put everything under the same square root. Right? If you divide the square root of this divided by that, it's the same thing as the square root of that divided by that. That's mathematical equivalence. So let's do that first. Then we can cancel 3, we can cancel R, we can cancel T, and that leaves us with molecular weight, or molar mass. Okay, so now the relationship is inverse, right? If the velocity of A is in the numerator here, the molecular weight of A is in the denominator there. That's Graham's law. That's interesting to me because Graham's law appears to be derived from a theory when usually it's the other way around. You get the law first and then you derive a theory from it eventually. But in this case, it looks like Graham's law was derived from the kinetic molecular theory of gases. So it went the other direction. Okay. So let's see, we're going to have an example here. Right. Hydrogen chloride, which is a gas, right? It's not in solution, so it has to be, it's a gas. And ammonia will react to produce ammonium chloride solid, which means if you let the two come together and meet, they'll produce a cloud of finely divided particles of ammonium chloride. And that's how we used to test our fume hoods. We just take concentrated ammonia in one beaker, concentrated hydrochloric acid in the other one, set them next to each other, concentrated hydrochloric acid will fume. You don't want to breathe the fumes because it'll choke you. And it only has to be, I think it was 37% hydrochloric acid. We put those two beakers in the fume hood together, and the fumes combine in air and make this solid. So you can see it. So when the fume hood is running, you can see the smoke come up and go right out like that. So you know it's running. That's more of an interesting demonstration than it is a quantitative value. When they actually test the hoods, they use a little fan with an anemometer. Anyway, we can compare the molecular weight of these two gases because we can see when they meet. So if we put one end, let's see, the distance traveled. I think I got this out of order. Hold on a second. Where is, well, there it is. There's the tube. So you got this glass tube or plastic tube, and you put a wad of ammonia soaked cotton in one end and hydrochloric acid soaked in the other end, and you measure where they meet. The distance traveled is proportional to their velocities, right? So that's why we can say distance ammonia traveled, distance hydrochloric acid traveled is proportional to their velocities. We can use D instead of V. And then that relationship is Graham's law. Right? So the distance, the ratio of the distance should be 1.463. That is, the distance hydrochloric acid should travel, let's see, this one should travel faster than that. Ammonia is a lighter gas. There you go. The ratio of these two distances, that distance there to this distance is 1.463. Okay. I think we've got a tube in the back. We could do that demonstration if we had time. Let's see. Oh, okay. So this is an example where we're actually going to compare ammonia with some halogenated compound so that you can get that interaction. We can see when they meet. If we do that, then we say the distance traveled for ammonia is this. So the distance traveled for the other one has to be 120 minus that because the tube is 120 centimeters long. So that's how we get those two distances. And that ratio then is equal to this unknown divided by the known ammonia. And we find out that the molecular weight then is 127 grams per mole. We just compare it to a list, right? It turns out to be hydrogen iodide. I don't know what this is. I've got a clue. That formula doesn't ring a bell for me. Okay. All right, one last example. Practical application of Graham's law. During World War II, remember the Manhattan Project, or at least from history, we're trying to develop the atom bomb. And the problem was uranium was a mixture of U-238 and U-235, predominantly. This was only about 0.5% of the total. This is the one that you need for a bomb. So how do you separate them? Well, we tried several different things. In fact, the government said, sky's the limit, no limit on price. We'll just print money until we get the job done. So they tried different ways, right? There was the magnetic sector, like this mass spectrometer. You just charge you convert these things to uranium hexafluoride. That way you can get it into a gas quicker because uranium is metal. Right? But if you make a fluoride gas out of it, then with a little elevation of temperature, you can make a gas out of it. So you fire this gas through an ionizer, you convert it all to ions. Now you can run it through a magnetic field and it'll bend it. Well, it'll bend this one more than that one because this one's heavier, right? And that's how you separate them. But that wasn't very efficient. You couldn't get a lot of it at a time. So they tried another way to do it, which wasn't very well developed at the time, was centrifuge. Right? You know, the heavier one will fly to the outside, a gas centrifuge. And then the 235 will stay closer to the center and you can suck it off, send it to another centrifuge and do it over and over and over and over again. That's what Iran's doing now to make their bomb. And they will have one. Probably before Biden exits, because he's enabling them. Anyway, that's a political statement. I better get back to science. Actually, I was wrong. I thought it was 0.5%. They're saying it's 0.72%. It's still very low. So that didn't work out too well either. But they spent money and they built big factories to find out. And it was a race. See, who could make enough to make a bomb first? Well, there was one factory. I used to live in Oak Ridge as a kid. Oak Ridge was just a small community called Black Oak Ridge for a while. Federal government came in and expanded the place, changed the name to Oak Ridge, turned it into an armed camp. That was before I moved there as a kid. And set to work on purifying uranium. And they built these huge plants. One of them, I think it was called K25. I think I got a picture of it here. Yeah, K25. There it is in Oak Ridge, Tennessee. This thing was so big, they had barbed wire fence around it and orders to shoot first and ask questions later. It was so big, they had a perimeter road, you know, so that you could inspect the fencing. But it was open to the public. So my family wasn't very rich. We did have a car. So for entertainment, we'd all pile into the car and take a ride around one of these big facilities. It takes about 20 minutes to go around the whole thing. And you can look at the factory from outside. So it was fascinating to kids. But this thing was virtually all filters. They used filters to access the separation ability of Graham's law, right? If U-235 hexafluoride had a higher velocity at the same temperature than U-238, which it does, then it will go through the filter faster, which means you can concentrate it on the other side. And then you can take that, concentrate it through another filter, and just cascade them until you end up with 90-95% U-235 at the end. So these are just stacks and stacks and stacks of filters. The problem was they had to find a filter that wouldn't corrode from this fluoride compound. They tried stainless steel and it just eat it up. Stainless steel didn't stand a chance. Fortunately, DuPont had just recently in the 30s had discovered and was commercializing Teflon, which was impervious to the fluorides. So they made their filters out of Teflon and just stacked them up. And this is the one that produced the U-235 for little boy. Okay, I've got some details in here. This is the guy that invented Teflon and blah, blah, blah. There's some more information about K25 at that location, that website, if you want to know more about it. But it was all based on Graham's law. Now, last statement, real gases. PV equals nRT is good for the ideal gas. And for for all of our work, PV equals nRT is perfectly fine. But those that are working with gases at non-ideal conditions, very high pressures or very low temperatures, you need correction factors in there, in that equation, in order to make it work in the real world. Right? And those correction factors were developed and published by van der Waals, Johann Dieterich van der Waals. And he got a 1910 Nobel Prize for his work in these gases. But his formula said that this is P, this is V, and there's nRT. So you only had to correct P and V. And these are his correction factors for pressure, right? You need to take into account volume and moles, and this empirically determined constant for the gas that you were working with. It's very specific. Similarly for this one, you need the number of moles and a B factor for your gas. If you do that, then the equation works under non-ideal conditions. This is van der Waals corrections. And that should be it.